Okay, so this is this window is open, and you click on this is the welcome to basic. So this is this window is open, and you click on this is the welcome to basic electronics virtual laboratory. You click on list of experiments. So it will shows the available list of experiments. So almost 17 experiments are there, and one additional experiment is also there. It is under development. So now we are going to discuss this first experiment, that is VA characteristics of diode. You click on VA characteristics of a diode. VA characteristics means volt ampere characteristics of a diode. So for this experiment, these are the available features, like the theory of this experiment related to this experiment. Then what is the procedure we have to follow while doing the experiment is also available. And we go for simulation. Then after completion of the experiment, we can also perform some quiz exams. We can also conduct quiz examination for students. And this is assignment. And these are the references. These references are this theory and procedure. So all these are framed using these reference books, reference textbooks. Okay. Then the first experiment, this is the theory. Here, okay, theory is not required, mark. Okay, this is procedure, and we directly go to simulation part. So theory part and procedure will discuss our class teacher, subject teacher, or course teacher, right? So the VA characteristics of a diode. VA characteristics of a diode. That is our first experiment in electronics devices and circuits lab. So here the diode can operate in forward biased, reverse biased. So the first experiment is part A, part B. Part A is forward biased silicon diode, reverse biased silicon diode. Part B, forward biased germanium diode and reverse biased germanium diode. So we have two different materials like silicon diode and germanium diode. And here this is you click on this forward biased silicon diode. The experiment will start from this point. That is, this is the experiment. Okay, this is the circuit diagram for forward biased silicon diode. So here the circuit is readily available with connections. So you need not to make any connections here. The circuit is readily available. If you want to make the connections, you choose this one. Forward biased, same forward biased silicon diode. Draw the circuit diagram. So what is the difference between these two? In the first case, these two are the same experiments only. The difference is here the circuit is completely available. All the connections are made. But here, if you want to make the connection between the components, you click on this forward biased silicon diode icon. Now the circuit is open like this. What is the difference between this one and previous one? Previous one, the circuit connections are made, but here the connections are not available. Suresh Garu, is it audible? Suresh sir, is it audible, sir?
Yes, clearly audible and clearly
audible, sir. Audible.
Okay,
sir.
Okay. Yeah. For the for experiment wise, the instructions are available. If you take any experiment in
Sir, in
EDC
the
lab,
excuse me, sir.
Sir.
Sir, in the screen there is some Siddhant's liver is failing. Some ad, sir.
Wait, sir. Yeah. 1 minute.
Right, sir.
I will. Yeah. I will close that.
Yes, sir. Okay. Thank you, sir.
Yeah. Okay. So each and every experiment, for every experiment, there are some instructions on the left side top. These are the instructions. Instructions is nothing but the procedure, how to make the connections and how to perform the experiment. How to make the connections and how to make the how to perform the experiment. Okay. Okay. So here you click on instructions. So what is the first one? Connect the components as mentioned below. As mentioned below, the first connection is L1 to L3, L1 to L3. So to make the connection between these two, you click on this one and drag to 3, drag and place. You click on 1, 2, 3. So in the first instruction, it indicates that make the connection between L1 to L3, then L4 to L7. This is L4 and this is L7. To make the connection between these two, you click on 4 and drag on to 7. Then the next connection is L8 to L10. So this is L8 and this is L10. So once again, you click on this and you can make the connections. Then the next one is L5 to L10. So these are the numbers. L5 to L10. This is L5 and this is L10. So you make the connection between these two. Then L6 to L11. This is L6 and this is L11. So then L9 to L12. 9 is here and 12 is here. You can make the connection. Then L6 to, one more connection is left here, L9 to L11. This one is last one. So like that we can make the connections. So one thing I want to tell you, so ready-madely the circuit is available. By opening that particular circuit, we can perform the experiment based on the procedure. That is one case. But the same experiment, so we can make the connections and we can perform the experiment later. Okay. So if you want to check whether the connections are right or wrong, so here there is a button. Is it visible, sir? Check connections. Check connections. You click on check connections. Yes, right connections. So the connections are right. If there is any wrong connection, there they mention it is a wrong connection. So if wrong connection is there, so we have to remove all the connections and we have to make connections once again. Okay. So set the resistance and input DC voltage. So to perform this particular experiment, there is some procedure. So here the first part is over, that is connections, connect the components as mentioned below, that part is over. Then we go for click on check connections. We already connections are checked. Then the third one is, what is the third one? If connected wrong, double click on the wrong connection. Okay, by double click on the wrong connection, else click on delete all connections. So button to erase all the connections. So we can delete that particular connection, or we can also delete the total connections. Then, so once the connections are over, then what is the next step? Select the diode. So here some diodes are available. You see the window. You see this window. So you select the diode. So we have different diodes are available. So here the diode is you can select any diode, like I am selecting IN4001. This IN4001 cut-in voltage is 0.7. Okay, 0.6. Okay, so we are selecting the diode. Then set the DC voltage. So by varying this voltage, we can measure the current through the diode with the help of this meter, and we can also measure the voltage across the diode with the help of this meter. So these two are important. This is current through the circuit and this is voltage across the diode. Okay, so if you know these two values for different input voltages, so we can draw the characteristics. So that is the procedure. Okay, so why we are drawing the characteristics of any device? To know the behavior or to know the characteristics of any electronic device. So we have to draw the characteristics. From the characteristics, we can estimate the performance of the device. You take any electronic device. So first we have to draw the characteristics to know the characteristics. How to know the characteristics? Just by drawing, by performing some experiment and by drawing the VA characteristics of the device. So from the device we can estimate the characteristics, or we can estimate the performance of the device. Okay, so here we are selecting IN4001 PN junction diode. Otherwise we can select any diode. So here this particular circuit is designed for different diodes. You can choose any one, no problem. So here I am choosing IN4001 diode. Its cut-in voltage automatically displayed here. It is 0.6 volts. Now by varying, this is the procedure by varying this voltage in step of 0.2 or 0.1 volts, note down the corresponding current and corresponding voltage, and all the values are tabulated here. One by one we can tabulate here. One by one we can tabulate here. Like that we can perform the experiment. So first I am applying 0.2 volts here. Just by varying this knob we can change the DC voltage. Okay, so now what is the value of this one? It is 0.3 volts. So this is the voltage, variable voltage, that corresponding reading or the corresponding value will available here. Here we are varying the voltage with the help of this knob. Okay, and first, before that, first we have to set the resistance value. First we have to set the resistance value. What is the value of resistance here? We can set one maximum value is, its maximum value is 2 kilo ohms. So we can set 1 kilo ohm, or we can set 500 ohms also, no problem. So now I am setting to 1000 ohms or 1 kilo ohm. 1000 ohm to, just by click on by select the resistance value, and by pressing arrow we can change the value. Now it is 1000 ohms. It is 1000 ohms is fixed. Just by varying this voltage with the help of this knob, this variable one, we can apply different values to the circuit. So each and every value, there is some circuit current and there is circuit voltage, that is voltage drop across the diode, and each value we can tabulate here. Then we can draw the flat. Okay, so the first value is for example is 0.2. You take 0.2. When input is 0.2, so what is the current, what is the circuit current, and what is the voltage available across the diode, we have to see. Then you click on add table, add to table. So for these values, what is the current? Voltage is 0, that is voltage across the diode is 0, and the current through the device is also 0. Why? Because the diode cut-in voltage is 0.6 voltage. Up to 0.6 voltage the current is a minimum, even though it may be 0 also in some cases. So when voltage across the diode slowly increases and the current increases exponentially. Okay, so you take another value, that is 0.2. You can take any value instead of 0.1 or 0.2. Now I am taking instead of 0.2 volts. So now it is 0.2 first value. Second value is 0.4 volts. 0.4 volts. You click on add to table. Okay, 0.4, 0.5. 1 minute. Very DC voltage. Okay, now it is 0.7. So input voltage is 0.7. Now the current is 0.1 millisecond. 0.1 millisecond. Add to table. Now the forward voltage is 0.3. So up to 0.3, sorry, below 0.53 volts, the current is almost 0. Now the current starts, that is 0.1. Then again vary the voltage. Now it is 1 volt. Add to table 1 volt. Now the current is 0.4 milliamps and the voltage across the diode is 0.539. Then change the voltage again to some other value, 1.2. Now it is 1.2. Then add to table. Now the voltage across the diode. So this value is this one, voltage across the diode, and this current is current through the diode. This one, this is current meter and this is voltmeter. Then change the voltage again. Now it is 1.5 volts. 1.5 volts. What is the voltage across the diode? It is 0.549, and now the current is 0.9 milliamps. So generally the forward current is in milliamps. Now change the voltage again to some other value. Now it is 1.8 volts. For 1.8 volts, So what is the voltage across the diode? It is 0.554 and the current is 1.2 milliamps. Suresh garu,
I request the participants, please unmute your mic. Yes, sir.
this
Yes, sir.
add to
Yes, sir.
table. It is 0.559 forward biased voltage. That is voltage across the diode is 0.559 and current is 1.6. So like that we can apply different values and we can add the values. Okay. So now it is 3 volts. 3 volts. The diode current is diode current is 2.4 milliamps. Diode voltage is 0.567. Then now change increase to input voltage. Now it is 3.5 volts. Now 3.5 volts and the diode voltage is 0.571 and the diode current is 2.9. So like that we can vary the input voltage and we note down the corresponding current and corresponding voltage and tabulate all these values here. And now the input voltage is 4.4 volts. For 4.4 volts, the current is 3.8 milliamps and the voltage across the diode is 0.77. So even though the input is 4.4 volts we are applying, but the voltage across the diode is 0.77 only. The difference voltage is available across the resistor. Okay, the difference voltage is available across the diode. So you change to another value. So now the input voltage is 4.9 volts. The voltage across the diode is 0.58 volts and the current is 4.3 milliamps and the final value. So here if the voltage is minimum value 0, maximum value 5 volts only. If you apply maximum value 5 volts to the circuit, what we get? The current is 4.4 milliamps. Add to table and the voltage across the diode is 0.581. So the minimum voltage is 0 volts, maximum voltage 5 volts. We get almost some 14 readings are available here. So this is the way of performing the experiment. After completion of the experiment, so we have to draw the VI characteristics. So for that, you click on this plot. If you click on this plot, it can draw automatically the VI characteristics of the diode by taking the voltage on x-axis and current is on y-axis. Okay, I will show you. You click on flat, go to the go down to the window. So this is the characteristics of the diode. So in the characteristics of the diode, this is volt ampere characteristics, voltage ampere characteristics. Okay, so voltage, diode voltage, this value is taken as x-axis and this current is this is taken as x-axis and this one is taken as y-axis. So this is VI characteristics of the diode. So after completion of the experiment, we can take the printout also. You click on this print. Now it is it shows all the items, that is circuit diagram, tabular form and graph is on one sheet. Wait, it is loading. Yeah, you can take the printout and you can place in your record also. So this is the first diagram. So this is the diagram, circuit diagram. Then this is the diode, type of diode and its cut-in voltage, then DC voltage and its resistance range, and these are the readings. So these are the readings. For these readings, this is the VI flat of the diode. Okay, we can save also. We can save and we can take printout and we can place in your record. So that is first experiment. Any doubts, ma'am? Up to this point, just now I completed one experiment, part A experiment. Any doubts you can ask. It is very easy, ma'am. Even it is easy than offline experiment, ma'am. Any doubts? Any doubts from faculty members or from students?
Thank you, sir. From students or faculty, if you are having any doubts, you can ask. Please unmute and you can ask.
Feel free, ma, no problem. You can ask any, even it is small doubt also, no problem. I will clarify your doubts, no issue.
Sir, this is Chandrasekhar, sir, faculty.
Yeah, yes, sir.
Good morning, sir. So here resistance is very, very high, no, sir? 1000 ohms means?
Yeah, you can reduce. That's why we get current maximum only 4.4 milliamps.
That's what,
You
sir.
can put it is a you can change, sir. You can change accordingly, no problem. You can change even 500 ohms. Actually, 1K is the highest value. That's why we get only minimum current 4.3 only. If you put 500 ohms here, we get maximum current under forward bias condition.
If it is 120 ohms means we will get the sharp current, no, sir, after breakdown voltage.
Yeah, sharp current will be more, but the cutting voltage is almost whatever the value you keep here.
That is okay, sir. Cutting voltage, that is okay, 0.6 volts, 0.5 to 0.6 volts.
Yeah.
If you are going to reduce the, okay, sir.
You can change, sir. So maximum available value is 2000 ohms or 2K. You can take any value between 100 ohms to 2000 ohms.
Okay. Thank you.
Okay, sir. Any doubts from students? Any doubts, ma'am? Okay. Shall I continue?
Yes, sir. Yes, sir.
Okay. So first one is first experiment is over. That is first part is over. Okay. So what we did so far, we take this circuit, this one, and we made the connections and we perform the experiment. Okay. In the next case, that is for reverse biased case, I am taking the ready-made circuit. Ready-made circuit. The circuit is the connections are made available. The connections are available just by selecting the diode. This is reverse biased case. Reverse biased case. So in the reverse biased case, either diode or supply voltage is reversed, but not both, ma. If you reverse both, again it is a forward biased diode. Now the diode is reversed. Already the connections are there. Okay. You select a particular diode. So earlier we selected IN4001. Now I am selecting IN4004. Okay. So actually under forward bias condition, so we have taken IN4001. Even for reverse bias also, we have to take same diode. Okay. So its reverse bias voltage automatically displayed. It is 30 volts. That means it can operate safely up to 30 volts. Up to 30 volts. So what is the maximum value here? They're given as 30.2. No problem. It is 30 volts only. We can vary the input voltage from 2 volts to 1 volt to maximum 30 volts. And this is the resistance value. Again, the resistance is maximum 2 kilo ohms. Normally, under reverse bias condition, only the leakage current is flowing through the circuit. There is no majority carriers current. Only minority carriers current is flowing through the circuit. So that theory part will explain you by your respective teacher. I am not explaining the theory part, ma. Okay. So here you choose this resistance value first. It may be okay. Now we are taking some 1500. 1500 or some 1000, because in the reverse biased condition the current is minimum. The current is in microamperes. So in the last one, the table is forward bias voltage versus forward biased current. Now it is reverse voltage to the reverse current. Okay. So just the procedure is same. The procedure is same. Just by varying this voltage, reverse voltage, note down the corresponding current and corresponding voltage. This voltage is nothing but voltage across the diode, same as previous one. This is current through the circuit, same as previous one. Okay. Now initially the voltage is for example 2 volts. This is 2 volts. 2 volts. Okay. You click on DC voltage, then press on arrow, right arrow, so that automatically the voltage will be variable. Okay. So input is 2 volts. The resistance is okay. It is you put it as 1K. 1 kilo ohms. Okay, approximately no problem, 1 kilo ohms. Okay, so here what is the current? Current is 0, and what is the voltage across the diode? 1.1 volt. So when input is 2 volts, the voltage across the diode is 1.1 volt, and the remaining drop is available across this resistance. Okay, add to table. So reverse voltage is 1.1 volt that is available across the diode, and the current is 0 microamperes. You change to some other value, some 3.85. You can take any value, no problem. 3.85, or you can take 4 volts because it is a reverse voltage. You can take large values, no problem. Take 4 volts. Yeah, for 4 volts input, what is the voltage across the diode? It is 2.3 volts, and still the current is 0. So add to table. So these values will be reflected on here in table. Okay, then vary the voltage. So some 5.9 volts. Now the current is started. It is 0.574 microamperes, and the voltage is 3.45. Add to table. 3.45 is the voltage across the diode, and 0.575 is the current microamperes. Then change the again input voltage to some other value. Then add to table. Now it is 4.43 voltage across the diode and 0.73 circuit current. Okay. Then change the input voltage to some 10 volts. Add to table. Then now the voltage across the diode is 6.07, and the current is 0.989 microamperes. Then change the input voltage. Now it is 13.8 volts. The voltage across the diode is 8.37, and current is 1.34 microamperes. Add to table. So like that, we can vary the input voltage, and we can see the values of current and voltage across the diode, and other value to current, and add to table. Okay, again change the value to some, that is 23.3. Now it's 27.1 volts, and the current voltages, and maximum we can apply 30 volts here. For 30 volts, what is the value? 18.9 volts is available across the diode, and the remaining voltage, the difference voltage, is available across 1.26 kilo ohms. So like that we can draw the okay, like that we can perform the experiment. So for various input voltages, these are the various circuit currents, and we can also plot the VI characteristics of silicon diode under reverse biased condition just by click on flat. We get reverse biased characteristics. Okay, so if you want to take printout, you press on print. So all the items, that is circuit diagram and diode details and tabular form and graph is also available on single sheet. We can take the printout and we can paste it in our record. So like that we can perform the reverse biased characteristics. Just here I am explaining the process, how to perform the experiment virtually. I am not explaining complete theory about PN junction diode under forward bias condition and reverse biased condition. Now all the items are available here. This is the controls, that is what is the type of diode and what is the maximum reverse voltage, and this is the circuit diagram, reverse biased condition circuit diagram, and this one is tabular form, and this is VA characteristics of the diode. Clear? This is first experiment. This is very simple experiment. The only minimum connections are required, right? Suresh sir?
Yes, sir.
Suresh,
Yes,
so
sir.
diode one experiment is completed. Shall I go for transistor?
Yes, sir.
Okay.
Sir, what are all the list of experiments available, sir?
Yeah, here VA characteristics of the diode one, half wave rectifier, full wave rectifier, with filter, without filter, GNR diode regulator is available, CB characteristics are available, CB characteristics are available, CE amplifier, frequency response of CE amplifier. These are the available experiments, sir. Sir, you can
Okay.
you can
Yes,
search
sir.
the remaining experiments in Google. You get all the experiments. Almost all the experiments are available in different websites, sir. That's all.
Okay, sir. Okay.
Okay.
Thank you, sir.
So
Thank you, sir.
I will move to I will move to amplifier.
Okay, sir.
Yeah, I think the amplifier, this is only for faculty, sir. Students, I think this theory not completed, na, sir. Okay.
Okay. Okay.
Yeah, you click on simulation. So now the experiment is BJT CE amplifier. You click on simulation. Again, here two circuits are available. One is CE amplifier. The second one is also CE amplifier. And if you choose this one, the circuits are readily available. Or if you choose this one, so we have to make the connections, right? So this is the CE amplifier diagram. See a CE amplifier diagram. So we have different RC components here. The components ranges are available here. Okay, you click on instruction. You click on instructions. So based on these instructions, we can apply or we can change the values. So what is the first one? The source voltage is set to 50 millivolts at 1 kilohertz frequency. It is already inbuilt. It is inbuilt. We need not to set input voltage at 1 kilohertz frequency. Then what about the second one? Keeping source voltage constant. So the frequency response of any electronic device is just by keeping the input voltage constant, by varying the frequency from very low frequency to very high frequency. What is the effect of frequency on output voltage? So that will give the frequency response of the amplifier. Okay, so here you set the source resistance as 100 ohms. So this is already designed. This is designed for these values. So what is the source resistance here? It is 100 ohms. Third point, sir, it is 100 ohms. So you click on source resistance and you make 100 ohms. So here, just by varying this knob, the value of this source resistance will be reflected here. Now it is 100 ohms. 100 ohms. Clear, sir? Then
Yes, sir.
what is the second? Yeah, what is the second one? Set collector resistance 4000 ohms. Where the collector resistance is available? The collector resistance is available here. It is 4K or 4000. Yeah, maximum 4000 only. 4000. Then what is the next value? So set emitter resistance 1000. Emitter resistance is 1000. You keep here, maximum value is 1000. Then set load resistance. What is the load resistance here? Value 2000. Now you keep maximum side 4000. Then set base resistance RB1 47K. This is RB1 47K. You keep here 47K. 47K, approximately 47. Okay. Yeah, exactly 47. Then what about the RB2 value? RB2 is how much it is? 10 kilo ohms. So you place 10 kilo ohms. It is 15K actually, 10 kilo ohms. Yeah, now it is 10 kilo ohms. So like that we can set the resistance value. Then we go for capacitance. So coupling capacitance is 10 microfarads. 10 microfarads. So by varying this, we can set the required value. Now it is 10 microfarads. Then what about the CC value? CC1 is 10 microfarads. Okay. Then CC2 also 10 microfarads. So all the capacitors are 10 microfarads only. Just by varying this knob, we can set the value. 10 micro, and this is also 10 micro. 10 micro. Okay. So initially it is set at initially it is set at 1 kilohertz. Why? Because So first we have to see whether the signal is amplified or not. Once signal is amplified, then we go for the frequency response of the CE amplifier. So we have to check both amplification as well as frequency response. Okay.
Sir,
So
excuse
this
me,
is the
sir.
experimental table.
Yes,
Yes.
sir. Load resistance is 2 kilo ohm only, no, sir.
Okay, no problem. We can say only 2K now.
Yes, sir.
Load resistance is yeah 2K. No problem. We can vary.
Yes.
We can reduce the load resistance. Now it is 2K resistance. 2 kilo ohms are 2000 resistance. Yeah.
Yes, sir.
Okay. So add to table. First we have to set the input resistance. Enter the input frequency. So okay, enter the input frequency. So we can increase the frequency in step of 50 hertz. In step of 50 hertz, 50 hertz, 1000, 50 hertz, 100, 150, 200, 250, like that. We can increase the frequency in step of 50 hertz. Okay, what is the maximum frequency available here? It is 50 kilohertz. 50 kilo or 50 mega it is?
50 mega, sir. 50 mega,
mega.
sir.
Yeah.
Yes, sir.
First, initially you said 50 H. Now it is 50 H. For 50 H of input signal, what is the magnitude of the input signal, sir? It is 50 millivolts. Okay, so 50 millivolts is inbuilt. Now the frequency is 50 H. What is the corresponding voltage? You add to table. What is the corresponding magnitude in dB? It is 10.559 dB. 10.599 dB. Even for supply voltage VCC, it is 12 volts internally. It is available. We need not to apply externally. This is inbuilt voltage. So for the 50 hertz frequency, for this 50 hertz frequency, what is the magnitude of gain? It is 10.599. So what is the formula for gain? Voltage gain is equal to 20 log of output voltage by input voltage. So this calculation is internally calculated, and finally it displays the corresponding value here. Is it clear, sir?
Yes, sir. Yes, sir.
Then we go for 100 hertz. 100 hertz. You apply 100 hertz. Then add to table. So at 105 hertz, 50 millivolts input voltage. Now the gain in dB is 16.70. Yeah, so it is 16.70. Then change the value to 200 or 220. You take any value, no problem. Add to table. Now it is 22.813. Then you take another value, add to table. Now it is 32.026. That means at 959 hertz, the voltage in dB 32.076. Kindly mute them, sir.
Yes, sir. Yes, sir.
Yeah, then change the frequency to some
సురేష్ గారు
Yes, sir.
సార్తో మాట్లాడొచ్చా? సార్తో మాట్లాడొచ్చా?
yeah,
Yes,
you
sir.
can
Yes,
talk,
sir.
sir.
Carry
You
on,
can
sir.
talk.
ట్రాన్సిస్టర్ నెంబర్ ఎంత సార్ మనం యూజ్ చేసేది ఇక్కడ? BC 107, BC 547 సార్?
Actually, they didn't give any transistor details, sir, actually, for this circuit.
ఓకే ఓకే సార్.
It is designed, it is having some number, but here it is not displayed. We will see in the instruction once again, sir. Not shown, sir. This one is not shown.
ఓకే ఓకే.
But in our earlier experiment, the transistor numbers are displayed there.
Right, sir. That's what. Because of the based on the transistor number, we'll get to some variations in the frequency, sir.
Exactly. Yeah, we get some variations because transistor to transistors, the amplification factors are different, na, sir.
Yeah,
We get different.
that's what, sir.
Okay. Yeah, we get different. Yeah.
Okay. Sir.
Yeah, thank you. So at 959, it is 32.0726. By varying this frequency, now it is 15K. Then we get 34. Then some 72.74. Yeah, we get some other value. So like that, we can vary the frequency By keeping the input voltage constant, then we get different readings at different frequencies. So this is the response. So these are the all the values that are tabulated here. If you want to plot the frequency response of this amplifier, you click on plot, we get the frequency response. So we all know that this is the frequency response of CE amplifier. So at low frequencies, gain slowly increases. Medium frequencies gain almost constant. At very high frequencies, due to inter-electrode capacitances or junction capacitance, again the gain decreases. The gain decreases. We can also we can also calculate the bandwidth also. This is the medium midband gain, lower cutoff frequency, higher cutoff frequency. The difference frequency is nothing but the bandwidth of the amplifier. So if you want to take the printout, again you can click on print and you take the printout. You can file it. Is it clear, sir? Any doubts now you can ask, sir. If you have any doubts, you can ask. Suresh, got any doubts?
Yes, sir. From the participants and student side, if you are having any doubts, you can ask. Sir, I'm having one doubt, sir. So with
You
which
can ask.
transistor, this circuit is designed? How we can say that, sir?
Actually, actually here the transistor is not mentioned, sir.
Yes, sir.
I think in the theory part it is available. I will check it. One second, sir. I will check it.
No doubt, sir. Transistor is NPN transistor, sir.
It is NPN
అక్కడ
transistor.
insert చేసింది NPN transistor, sir. కాకపోతే NPN transistor లో
Sir asking about number, sir. Transistor number. Actually,
Number, sir.
here the transistor number not mentioned. Not mentioned. Even theory part also not mentioned, sir.
Yes.
okay.
Okay,
Sure.
It is operating in NPN transistor only.
Yes,
This
sir.
is NPN only, na?
NPN only.
NPN only, sir. NPN. Okay, no doubt.
Yes.
But transistor number is not mentioned, sir. That is the issue. Okay. So like that
Okay,
we
sir.
can perform the experiment. Is it clear, sir?
Okay. Yes, sir. So from student side also, if you are having any doubts, you can ask.
వాళ్ళకి ఇంకా యాంప్లిఫైర్ దాకా వెళ్ళలేదు సార్. వాళ్ళు డయోడ్స్ లోనే ఉన్నారు.
Just connections,
Okay,
sir. Regarding
Okay,
connections only.
అందుకని వాళ్ళకి ఓకే.
Yeah. Only connections, sir. Connections and a procedure. I am asking only procedure.
Yes, sir.
Regarding procedure, you have any doubts, you can ask me. So sir will explain theory part in the classroom.
Sir, I think there are no doubts. I think so, sir.
Last experiment, sir. I will perform one more experiment and I will finish it. Okay.
Okay, sir.
Shall I continue? Actually, we started at 10:30, sir. 10:30.
Yes, sir. Yes, sir. Please, sir. Sir, may I know what are the lamps available, sir?
Yeah,
What are
I
the
will
lamps?
give information. Labs are this STLD lab is available, sir.
Okay, sir.
Second year complete labs are available, sir. Both two labs are available. EDC lab and STLD is available. Even DSP is also available.
Okay, sir.
Almost all the labs are available, sir. Only some experiments are available, some experiments are not available. That's sir.
Okay, okay.
At least 50 to 70% experiments are available, sir. You take any laboratory.
Yes, sir.
50 to 70% of experiments are available.
Okay. Thank you, sir.
Yeah. And finally, one more experiment I will explain and I will close the session. Okay.
Yes, sir.
I want to explain again. Okay. GINA diode, sir. GINA diode. So this is is GNR diode voltage regulator. So experiment wise, basic information is available, sir. That is,
Okay.
theory part is available, procedure is available, and this is a simulation. And we can also conduct quiz examination for students also after completion of the experiment. Then assignment is also available, some reference textbooks. Okay, so you click on simulation. Again, this window is open for this experiment, and here a GNR diode line regulation, GNR diode load regulation, and GNR diode characteristics. Actually, three different experiments. Okay, line regulation, load regulation, and basic characteristics of the GNR diode. Okay, so this is GNR diode line characteristics without connections. This is GNR diode load regulation without connections. This is readily available. Ready-made circuit is available. So all the connections are available here. We need not to make the connections. If you select that particular one. Okay, so GNR diode line regulator. So we know that this GNR diode acts as a voltage regulator. It gives constant voltage irrespective of changes in input voltage or line voltage, load voltage, or temperature. Okay, so this is the circuit diagram for GNR diode line regulator. Line regulator, line is nothing but input. Input is variable, load is fixed. Input variable and load is fixed. This is GNR diode. GNR diode. So here first we have to choose the GNR voltage. Here the GNR voltage is available from 3.3 volts minimum voltage to maximum 10 volts. Sir. Is it clear, sir? Sir, is it clear? Is it audible or
Yes,
not, sir?
Yes, sir. Audible, sir. Audible, sir.
GNR voltage
Yes.
is available from 3.3 volts minimum voltage to maximum 10 volts. You can choose any value between these two, that is 3.32 and 10 volts. Here I am choosing some 6.7 volts. So if you choose 6.7 volts, if you apply maximum voltage, even input voltage is 30 volts, it will not change because it acts as a voltage regulator. When you change the input voltage from minimum value to maximum value, it won't change the diode voltage. So here it is, VDC is 30 volts, but the diode drop is 6.7 only. The diode voltage is 6.7. If you take some 13.2 volts, still it is 6.7. You take any value that is 22.4, still it is 6.7. You take some 10 volts, still it is 6.7. So whatever the input voltage, the voltage, the GNR voltage is constant, but the circuit current will change. The circuit current will change. So what is the first step? So first we have to see the instructions. Set the GNR voltage first step. So already we set a GNR voltage as 6.7. With the help of this knob, we can set as 6.7. Then what is the second step? Set the series resistance value. So by varying this one, we can set the series resistance value. So for example, it is 1 kilo ohm. It is 1 kilo ohm. So input resistance or series resistance is set as 1 kilo ohm. Then we go for again instruction. Now vary the set the load resistance. We can set any load because it is a line regulation, irrespective of the load, irrespective of the input voltage. So it gives the constant value. You fix any load resistance with the help of this knob. So here I am putting it put it as some 4 kilo ohms. So your source resistance or series resistance is 1 kilo ohm and load is 4 kilo ohms. Just by varying this voltage, so we can observe the GNR voltage, whether it is maintaining constant or is there any deviation. That shows the line regulator. So what is the minimum voltage is required, sir? Anyone? Any faculty, sir? What is the minimum voltage required to operate the GNR in reverse breakdown region, sir? For 6.7 volts GNR? Anyone? Sir, anyone? Sir garu? Sorry, Suresh garu.
Yes, sir. Yes, sir. Hello, sir.
What is the What is the minimum input voltage required to maintain the 6.7 volts, sir? It should be 6.7, at least minimum 7 volts. If it is less than 7 volts, so it is not into the breakdown region. It is simply reverse bias only, just like it is ordinary diode. So you check it. For example, it is how much it is? It is only 2 volts. For 2 volts, you add to table. What we get? The regulated voltage is only 2 volts. Regulated voltage is 2 volts. Regulation percent is 100% regulation. Then you take another value, some 3.8 volts. Again, it is less than 6.7 volts. It gives 3.8 volts only. Then you take another value, 6.8. So what is the value now? It is 6.7. That means if you choose the diode voltage, GNR voltage as 6.7, our input voltage should be at least minimum 6.7 only. Then only we get GNR voltage 6.7. If you take GNR as 8 volts, the minimum voltage required is 8 volts. If you take 10 volts GNR diode, the minimum voltage required is 10 volts. Okay. So for 6.8 unregulated input voltage, this is the load current, and this is the GNR current, and this is the regulated voltage. So like that we can apply different values. Now the voltage is 9.2, add to flag, now it is 6.7. Next, change the input voltage, add to table, now it is 6.7. So change the value to some other, change the DC value, then apply, add to table, then it is again 6.7. Even though we are applying 14 volts at the input side, what we get? We get 6.7 volts GNR voltage. You change the DC voltage again, then to some 17.6, add to table, we get how much? Same 6.7. You take another value, that is 21.4. The GNR voltage is again 6.7. Then change the DC value to some other value, again we get 6.7. So from the characteristics, what we observed is when input is greater than or equal to the 6.7, the voltage remains constant. But current drastically increases. Current is drastically increases. So if you take the maximum value 30 volts, add to table, what we get? For 30 volts input voltage, 6.7 volts only output voltage, 6.7 volts output voltage, but the current is 23.3 milliamps. 23.3 milliamps. So once the experiment is over, then to draw the regulation, this is 6.7 volts, and 6.7 volts we selected GNR diode. Then this is the series resistance 1 kilo ohm. This is the load resistance 4 kilo ohm. So for line regulation, this is constant, load is constant, only input is variable. Then we can draw the plot the characteristics. This is the characteristics of the line regulation characteristics. So line regulation means source voltage is taken as x-axis, output voltage is taken as y-axis. Below the GNR voltage, there is a linear region voltage. Then once the input voltage is greater than or equal to GNR value, it maintains the constant value even though input voltage varies from 6.7 to 30 volts. So this is the regulated diagram. This is the line regulation. Like that we can perform load regulation also. In load regulation, line is fixed, load is variable. That's all. So by changing the load value, we can verify whether it acts as a voltage regulator or not. So these are the readings. So circuit diagram, basic information, and this one is different values, and this is the graph. Any doubts, sir? Sir, any doubts from student side or faculty side?
Yes, sir. Yes, sir. Thank you, sir.
Here
So-
also GNR diode number is not mentioned, sir. Am I right?
Yes, sir.
Diode,
Yes, sir, yes.
diode is not mentioned. We can choose the required value from 3.3 to maximum 30 volts. Accordingly, we can vary the input voltage, we can note out corresponding readings, and we can plot the line regulation.
Yes.
The line regulation.
No,
Sir.
no, sir. The GNR number is The depends on the breakdown voltage only, no, sir.
Yeah, so, but it is having some number also, na sir? So number is there, na Zener diode?
Yeah. On that number it indicates
6 point.
that gives the.
Yeah.
Yes, sir.
Yeah.
There is no.
Zener
There is
Zener diode.
no. There is no separate number for Zener diode, sir. Zener breakdown gives
Okay,
the itself a number.
There is one letter is also there, sir. Some letter with some breakdown voltage.
Yes, sir. The breakdown
Some company
voltage
name.
gives the. Suppose Z
Zener,
7.8.
that shows. You speak, sir. You speak.
Z 7.8 means that is the breakdown voltage 7.8 volt. The number itself is the Z 7.8. There is no separate number for Zener diode like PN junction diode 1N4001 1N4007 like that.
Available, sir. Zener diode number is there.
1 minute.
Zener
Number is available, sir.
Number available, sir. That 1N4007, I think so, sir. That is.
It is the PN junction. General. No, sir. General diode number. That is.
Sir, 1 minute. Sir, please 1 minute, sir. 1 minute. Number is available, sir. Number with breakdown voltage is available.
Breakdown voltage is available.
Okay.
Based on the breakdown voltage only, the Zener number gives.
Any doubt?
Students, please unmute your mic.
So from student side, no doubts now? Nobody is asking.
Student side, if you are having any doubts, you can please ask. Yes, sir. There you can see, sir, 1N4730 number, diode number.
Creating some noise.
Yes, sir. Yes,
Is it okay, sir?
Yes, sir.
Yeah.
Still, any more doubts from the participants or from faculty
Any
or
other
students?
doubts?
You can ask. Chaitanya.
You can ask, sir. Both from faculty and students. You can ask. Any doubts? Chaitanya Kumar. I think quickly.
Yes, sir. 242, Chaitanya Kumar.
Any doubts?
If you are having doubts, you unmute yourself, or else you mute your mic.